great and violent power of nuclear explosions can be used for peaceful purposes. We call this project Plowshare. The reason for the name is obvious. For quite a few years in the Livermore laboratory, we have tried to find ways to bend this power to useful purposes. Geographical engineering, move great amounts of earth, build canals, harbors, use nuclear explosives, like high explosives have been used, for the purpose of mining. Use nuclear explosives in the bowels of the earth, using the earth itself as the crucible to make new kinds of chemistry. These are just some possibilities. Here I have with me a piece of salt from a mine in New Mexico. There, in the GNOME site, we have performed an explosion to find out the behavior of nuclear explosives in this new medium, salt. And we performed that explosion for peaceful purposes alone. We try to find out whether we can deposit great amounts of energy in the salt and then extract it later for useful purposes. We built up a physics laboratory right down there in the salt mine to find out more about the neutrons which make nuclear explosives and nuclear reactors stick. We try to do the best to develop further this great tool, nuclear energy, for peaceful purposes. But at the very outset, we were convinced of one thing. The most interesting thing that we might find out may be something which no one expects, a surprise.
March 1958, the Atomic Energy Commission requests the United States Geological Survey to study the many salt formations within the continental United States and determine which of them would be of sufficient depth for containment of the proposed explosion in a region of low population density, on federal land, and contain salt of desirable purity. The study suggests that the general area of the Delaware Basin in southeast New Mexico, where the salt lies between a 700 and 1,500-foot depth, best fits the criteria. A survey is undertaken. A site about 25 miles southeast of Carlsbad is selected. It's rather flat, with a distinct desert-like beauty. The nearest habitations are 2 ranch houses about 5 miles away. The ranchers who live in them lease some of the federal land for cattle grazing. The closest town, the small community of Loving, is about 12 miles away. The main industry of the area is potash mining and refining, and the nearest underground facility is 8 miles away. Safety of people, homes, industrial facilities, of the environment itself is a primary consideration in deciding whether the explosion can be carried out. As the first step in the safety program, the Atomic Energy Commission selects from a panel nominated by the National Academy of Sciences, experts in the fields of geophysics, hydrology, and seismology to assess the extent of ground disturbance. Assured that the experiment could be conducted without damage to the surrounding facilities, the Atomic Energy Commission directs the Lawrence Radiation Laboratory at Livermore to complete plans for the project. When all the information is assembled and ideas put on paper, the laboratory's computer facilities are applied to problems posed. Using an underground nuclear explosion code, many simulated detonations are performed mathematically to help establish construction criteria for the safe containment of a 5-kiloton explosion, the equivalent of 5,000 tons of high explosives. The emplacement of the nuclear device is planned for the center of a salt formation whose upper layer is at 710 feet, with overburden consisting primarily of sandstone, shales, anhydrites, and claystone. A shaft is to be driven to a depth of 1,200 feet, and at that level, a 1,000-foot tunnel ending in a small room would be dug. The tunnel is expected to seal itself after the detonation. For experiments in neutron physics, a vacuum pipe will extend from the shot room to a pair of rotating wheels near the bottom of the shaft. Foils of selected metallic isotopes mounted on the wheels are the neutron targets. A large concrete block with a slot through it will channel a narrow band of neutrons to the targets, the neutrons striking the foils as they pass. In the nuclear explosion, an extremely large number of neutrons is emitted. A small fraction of these will be intercepted by the vacuum pipe and travel toward the targets. Since these neutrons possess a range of energies, they travel at different speeds, striking the targets at different times. They register a characteristic radioactive imprint, depending on neutron energy and the nuclear properties of the element selected as target materials. Before one complete revolution of the wheel, a specially designed shutter will close, terminating the exposure. Holes drilled from the alcoves along the tunnel will house instruments for close-in measurements, such as pressure profiles, earth motion, temperature, peak pressures, and particle velocity profiles. The predictions show that a few millionths of a second following detonation, the explosion energy will fill the room. The material in the room will be at an extremely high temperature and pressure. This high-pressure gas will push on the walls and start a strong shock wave through the salt. About 100 tons of salt will be vaporized, assisting to further enlarge the cavity. 40% of the energy released will be captured in molten material and collect to a depth of 35 feet at the bottom of a 110-foot diameter cavity. A mechanical system on the surface is designed to control the flow of gas and fluid media from boreholes, which will extend to the detonation zone. Temperatures and flow rates of the steam created in the cavity by the explosion and by the subsequent introduction of water will be recorded. The system will also provide for the recovery of isotopes and removal of condensable gases. March 1960, the Atomic Energy Commission approves construction plans and site preparation. A local headquarters is established in Carlsbad. Mining operations begin to create a laboratory deep beneath the Earth's surface to study the peaceful application of a great force. A force that had its violent birth at nearby Alamogordo. As scientists at the GNOME site prepare another advance toward the unknown, the life of the modern West goes on as usual. The legendary Pecos River, once the scene of giant cattle drives, is a precious source of water for agriculture, power, recreation. A major industry of the area continues to flourish. Thousands of tourists descend into the darkness to view the wonders of Carlsbad Caverns. But tourists were not the only ones moving into the earth. 35 miles away at the GNOME site, miners continue operations to create another cavern. Other facilities are constructed and assembled. From nearby oil fields, drillers come, but not for oil. Employing the same drilling equipment and techniques as those used in sinking an oil well, holes are made to accommodate cables and instruments. A head frame is erected over the shaft to facilitate mining at greater depths. The salt formation is reached. The constant removal of material is a visible measure of the miner's progress. 14 months after start of excavation, they reach the proposed ground zero. Other contractors move in to establish the center of operations for technical personnel. Cables laid on the surface are routed from recording locations to points near future instrument sites. More than 100 miles of cable are laid in the most thoroughly instrumented underground nuclear experiment yet undertaken. Most cable is introduced into the tunnel through the shaft. A separate drill hole accommodates cable for instruments near the shot point. Here, the signals are expected to be of extremely low intensity and must be isolated from electrical interference in the tunnel at shot time. It takes skilled engineering to drop 12 tons of cable down the 1,200-foot drill hole. The construction crews have paved the way. From the various scientific laboratories, field trailers converge on the test sites, mobile recording stations, machine shops, photo labs, and offices. Scientists and technicians join the steady stream of workers preparing apparatus for installation underground. It would take hundreds of years in a laboratory to duplicate the great number of neutrons released by this explosion. Los Alamos Scientific Laboratory and the Lawrence Radiation Laboratory at Livermore set up their apparatus for a simultaneous experiment in neutron physics. Meanwhile, the assembly of the surface plant for the steam power and gaseous isotope measurements program proceeds. A spray pond will supply the coolant for the heat exchange system. A large tank is provided for storing condensed, contaminated steam flowing from the cavity through boreholes. The technical phase of Project GNOME goes into full swing. Installation of scientific instruments commences. Electronic instrumentation packages are placed in holes, and containers filled with a variety of chemicals and minerals, supplied in part by interested industries, are installed at various distances near the device room to permit later study of the effects of strong shock waves upon the materials. From the electronic instruments, cables are tied into the trailers where the signals will be recorded on film and tape. The event is rehearsed and signals simulated repeatedly. Hours of checking and rechecking are spent to establish the pattern of signals expected. Much of the data will appear as very fast traces on oscilloscopes and be recorded on film. After each dry run, the films are processed in the mobile photographic laboratory. A study of the waveforms permits technical personnel to calibrate the instruments and evaluate the performance of their equipment. The Department of Defense takes advantage of the opportunity presented to gather information for its VILA uniform program to improve methods of detecting and identifying underground nuclear detonations. As part of the physical effects program, groundwater studies are started. A number of test drillings within a 15-mile radius are made before the event, and a sampling program will be conducted on a monthly basis for several years following the detonation. Besides close-in stations, remote seismic stations are installed at nearby mines and communities, including one in Carlsbad Caverns. A representative of the United States Coast and Geodetic Survey explains to a ranger how their sensitive instruments measure disturbances within the earth. In keeping with the open nature of the events, others are invited to record the signal on a worldwide seismic network. November 1961. The apparatus at Surface Zero is fully assembled and checked out. Everything is in working order. The site of Project GNOME is ready for its role in man's quest for knowledge. The emplacement and firing of the nuclear device waits only the final authorization of the nation's chief executive. Newsmen and representatives from industry and scientific laboratories are invited to inspect the site. Some 350 observers, including those from 9 foreign countries, attend. For like all plowshare projects, the scientific goals and results of Project GNOME are to be available to everyone. With the exception of the shot chamber, which will soon house the nuclear device, visitors are allowed to inspect all phases of the installation. Radio and television carry extensive accounts of the planned event. Observers are briefed on the methods to be used for power and isotope measurements and the extraction of samples from the detonation zone. A few days before shot time, all livestock in the area are removed to pasturage outside a 5-mile radius from surface zero. Except for miscellaneous pipe and the large tank, the power and isotope recovery surface plant is dismantled and removed to avoid damage from ground shock. The nuclear device is now emplaced in the shot room. Final preparations begin. Final checkout of the electronic systems continues until every criteria is satisfied. The 3 trailers which house the electronics recording equipment remain. The rest are removed back to the control point. 1.5 miles from ground zero, 2,400 pounds of TNT are emplaced to be fired shortly after the nuclear explosion to permit a comparison of the atmospheric effect from the known amount of TNT with the atmospheric disturbance caused by the underground detonation. 3 inertial camera stations are set up at various distances to measure surface motion. Controlled remotely, high-speed cameras will record displacement of grids with respect to suspended weights. From 4,000 feet, cameras with long telephoto lenses will film in slow motion prefixed targets to measure surface displacement. Directly over ground zero, an isotope prompt sampler is set up to capture isotopes emerging through a vacuum pipe from the shot room. The control point, located 4.5 miles from surface zero, is now the center of operations. No one will be permitted closer at the time of the explosion. D-1. All is in readiness. Shot time is just hours away. It is dawn. Observers arrive. The countdown is started. Helicopters wait to fly scientific observers and official photographers over the test area. Newsmen set up on a nearby rise that affords a good view. As a measure of public safety, the United States Weather Bureau staff provides continuous reports of weather data and fallout predictions. They report early morning winds are unfavorable and shot time is delayed. Constant surveillance of the test area is maintained. By 11 o'clock, the local winds shift. Countdown is resumed. Within the timing and firing trailer, Experienced eyes scan instruments, searching for signs of trouble. The test director coordinates the advance toward H hour. The test can be halted up to the last second.
15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Immediately following the detonation, observers at the control point experience a noticeable earth tremor caused by the shock wave. Immediately after, the 2,400 pounds of TNT are detonated prematurely. Aerial observers report only minimal damage from the underground nuclear detonation to surface facilities. However, soon after, an unexpected high level of radiation is registered at the bottom of the shaft. 7 minutes following the explosion, white vapor emerges from the shaft. The United States Public Health Service Air Monitoring Team begins air sampling missions to determine the extent of any radiation off the site. Many were curious about the venting, what had caused it. The steam in the cavity apparently escaped through cracks into the tunnel and up the shaft, carrying with it the radioactive gases. Although the possibility of the escape of gaseous radioactive steam was remote, the project personnel are prepared for such an emergency, and all the precautions taken pay off. Minor amounts of radiation released soon dissipate, and no harmful off-site contamination is reported. When the radiation level is within prescribed safety limits, re-entry teams from the technical programs recover valuable records from the trailers near the shaft. Thorough checks are made to determine possible exposure. Each individual carries dosimeters to record the amount of radioactivity he receives. No exposure exceeds the limits established. The following day, a check shows no radiation at surface zero. Work crews initiate post-shot projects. The inertial camera stations perform as expected. Vela Program's geophones provide a dramatic record of the noises beneath the Earth during and following the explosion. The buzzing sounds over the Earth noises are from helicopters flying overhead. The surface above ground zero had risen a maximum of 6.5 feet, while 100 feet away, only a half a foot displacement is recorded. Within 2 days, re-entry drilling operations start. Meanwhile, preparations to re-enter the shaft begin. On the 6th day following the event, radiation levels at the bottom of the shaft had decreased enough to allow recovery of the neutron wheels. At various laboratories, the painstakingly slow evaluation of the results gets underway. Drilling operations continue. Blowout preventer valves are used in the event there are high-pressure gases. The drill breaks through the top of the cavity at about 1,100 feet. No high pressures are encountered, and temperatures are of the order of 200 degrees Fahrenheit. Additional drill holes indicate that the salt had broken from the top and sides of the cavity, causing the molten pool of salt at the bottom to solidify. Therefore, only a limited thermal measurements program is possible. Temperature pockets in the rubble zone are as high as 1,450 degrees Fahrenheit, near the melting point of salt. Core specimens are collected and placed into special shipping containers for laboratory study of isotope content and for clues they contain regarding the behavior of the medium near the nuclear explosion. 6 months later, the cavity is reached through a drift mine parallel to the original tunnel. Exploratory probes are made and the cavity found safe to enter, allowing scientists to acquire data by direct observation and inspection of this spectacular man-made wonder. Radiation levels are only 5 milliröntgens, but cavity temperature registers an uncomfortable 140 degrees Fahrenheit. The energy released by the nuclear explosive was determined to be about 3 kilotons. The intense heat generated melted about 2,400 tons of salt, quickly cooled by partial collapse, which filled the lower half of the cavity with 28,000 tons of rubble. This enormous cavern measures about 170 feet across and is almost 90 feet high. Here, 1,200 feet beneath the Earth's surface, this underground laboratory was open for inspection to official observers and members of the press, where the phenomena from a contained nuclear explosion is being studied.
GNOME has given us a great deal of information. Some of it is still underground. We'll have to dig for this additional information. Some of it is available now. We expected to make a cavity. We did make a cavity. 1 million cubic feet. It stood up. It's standing now. Our investigation of the atomic nucleus gave us a challenging new fact. We know that nuclei have sharp energy levels. We now know that these energy levels come in groups having similar properties. Earthquake waves from GNOME traveled, but not quite at the expected speed. To the east, they arrived with a different speed than we expected, and in intensities 30 times as great as we thought they would be. This means something about the layering of the Earth in the Mississippi Valley, which we did not know before. We had our surprise. A great deal of water vapor was released from the cavity. We thought it might happen. It did happen. This makes it much harder to confine energy. It makes it much easier to extract some kinds of isotopes, and isotope extraction is one of our major purposes. And here is a real hope for the future. Underground explosions will make, and we know how to make them, great deal of new isotopes of new elements. A whole new realm of chemistry beyond the element plutonium is going to be opened up much more widely than it has been opened up ever before. But looking even farther into the future and disregarding the immediate results, our steady work gives one certain expectation. We are perfecting our tools. We are ridding our tools for the association with radioactive danger. The time is not distant when such explosions can be made for the benefit of mankind without undue hazard, just in the same way as we are using high explosives today.